On December 7, 2020, China's Chang'e 5 lander detected a subsurface structure beneath the moon, 2.3 kilometers wide, 300 plus meters deep, with perfect right-angle corners and uniform 12-meter layers. The geometry was so inconsistent with natural formation that China delayed releasing data for 7 months. The findings challenge fundamental assumptions about lunar geology and the moon's formation, and contradict what Western agencies have claimed for half a century. What if the moon isn't the dead, inert world described since Apollo? What if Chinese instruments reveal it remains partially molten, with surface chemistry that shouldn't exist under current theories? What if decades of Western lunar science were built on incomplete data and geopolitical motivations? Today, we examine the discoveries from Chinese lunar missions that have quietly revolutionized our understanding of the moon while receiving minimal coverage in Western media and academic publications. These findings don't just refine our knowledge, they fundamentally contradict core assumptions that have guided planetary science for 50 years. Prepare yourselves. We begin. The controversy starts with something as basic as the color of lunar soil. Every image from the Apollo missions, every NASA press release, every museum display shows the moon's surface as uniform gray, a monochromatic landscape of gray rocks, gray dust, and gray horizons extending to infinity. This chromatic uniformity became so deeply embedded in public consciousness that when the Chang'e 3 lander transmitted its first high-resolution color images in December 2013, and then Western scientists initially assumed the Chinese cameras were malfunctioning or improperly calibrated. The Chang'e 3 images showed soil that wasn't gray at all. The regoliths surrounding the landing site in Mare Imbrium displayed distinct brownish-red coloration in natural lighting conditions, with spectroscopic measurements confirming the color represented actual material composition, rather than instrumental artifact or lighting effects. The Jade Rabbit rover's panoramic cameras captured landscapes featuring chocolate-brown soil, reddish rocks, and surface materials, showing color variations far more dramatic than anything visible in Apollo photography. This chromatic discrepancy raises an uncomfortable question. Why do Apollo images show monochromatic gray, while Chinese images show distinct colors? The official explanation focuses on camera technology differences, lighting conditions, and color balance calibration. However, independent analysis of the original Apollo film, negatives by researchers at Beijing Normal University, revealed something disturbing. The negatives contain color information that was systematically desaturated during NASA's processing and publication, reducing the visible color range to create the familiar gray appearance. The raw film actually captured browns, tans, and subtle color variations remarkably similar to what Chang'e missions later documented. The implications are staggering. For 50 years, the public has been shown processed images that suppress the moon's actual colors, creating a false impression of chromatic uniformity. On whether this processing resulted from technical limitations of 1960s era printing technology, aesthetic choices by NASA's imaging team, or deliberate policy to create a specific public perception remains unclear. What is certain is that the gray moon of popular imagination differs substantially from the variegated reality revealed by modern Chinese instruments. But the color controversy represents merely the surface of deeper contradictions. The Chang'e 5 mission's sample return in December 2020 brought back 1,731 grams of lunar material from Oceanus Procellarum, the first lunar samples returned to Earth since the Soviet Luna 24 mission in 1976. Initial analysis of these samples at the Chinese Academy of Sciences revealed ages clustering around 1.97 billion years, making them by far the youngest lunar basalts ever studied. This age determination was so unexpected that the research team repeated the analysis using 3 independent radiometric dating methods, all confirming the same result within measurement uncertainties. The significance of this age measurement cannot be overstated. NASA's analysis of Apollo samples established a lunar chronology, suggesting that volcanic activity on the moon essentially ceased approximately 3.1 billion years ago as the lunar interior cooled and solidified. This timeline has been taught in every planetary geology course for decades, creating a scientific consensus that the moon has been geologically dead for over 3 billion years. The Chang'e 5 samples demolish this consensus entirely, proving that lunar volcanism continued for at least another billion years beyond what Apollo samples indicated. The discrepancy raises an obvious question. Why did Apollo samples, collected from 6 different landing sites across the lunar near side, all show ages greater than 3.1 billion years, while the Chang'e 5 samples are only 1.97 billion years old? The conventional explanation suggests that Apollo landing sites were selected for safety rather than geological diversity, potentially biasing the age distribution toward older terrains. However, this explanation fails to account for why NASA's orbital observations and theoretical models of lunar thermal evolution never predicted that such young volcanic deposits existed. Critics of NASA's lunar science program suggest a more disturbing possibility: that the agency's commitment to a specific narrative about the moon's geological death may have influenced site selection, sample analysis, and theoretical modeling in ways that reinforced preconceptions rather than testing them objectively. The Chang'e 5 discovery demonstrates that China's approach, selecting landing sites based purely on scientific interest rather than political or safety considerations, has uncovered phenomena that NASA's Apollo program missed entirely. The ground-penetrating radar data from Chang'e 3 and Chang'e 4 rovers revealed subsurface structures even more controversial than the age discrepancies. The U2 rover carried a ground-penetrating radar system capable of mapping subsurface layering to depths of approximately 400 meters using electromagnetic pulses at frequencies of 60 and 500 megahertz. As the rover traversed Mare Imbrium, the radar painted a picture of subsurface structure that contradicts everything we thought we understood about lunar Maria formation. The conventional model, based entirely on Apollo-era data and remote sensing, describes the lunar Maria's ancient impact basins that filled with basaltic lava flows between 3.9 and 3.1 billion years ago. These lava flows should appear in radar data as relatively homogeneous layers, with smooth, continuous interfaces representing individual eruption episodes. The Chang'e 3 radar showed something completely different. Instead of smooth, continuous layers, the subsurface structure revealed by Chinese instruments shows extraordinary complexity, with at least 9 distinct layers in the upper 400 meters, many exhibiting irregular boundaries, discontinuous segments, and embedded structures that appear geometrically inconsistent with lava flow emplacement. One particularly anomalous structure, at a depth of approximately 240 meters, shows a rectangular cross-section measuring 80 meters by 120 meters, with radar reflective boundaries suggesting different material composition than the surrounding basalt. Dr. Li Chunlai at the National Astronomical Observatories of China, who led the radar data analysis, published findings in Science magazine describing these subsurface anomalies, but notably avoided speculating about their origin. The paper's abstract uses carefully neutral language. The radar profiles reveal a complex geological structure that suggests a more dynamic volcanic history than previously understood. The diplomatic phrasing obscures a more dramatic reality. The structures don't match any known volcanic features and appear more consistent with deliberate excavation or construction than with natural lava emplacement. Western researchers have largely ignored these radar anomalies, with published responses focusing on technical critiques of the radar's resolution and interpretation methodologies, rather than addressing the fundamental question of what could create such geometrically regular subsurface structures. The silence is deafening, suggesting an unwillingness to engage with data that doesn't fit established frameworks. The discovery of the mysterious gel-like substance by the U-2 rover on the lunar far side in July 2019 generated brief international attention before being quietly buried under layers of technical jargon and bureaucratic opacity. The rover's navigation cameras spotted an unusually colored material in a small impact crater during traverse planning, The material appeared to have a different reflectance and texture than surrounding regolith, prompting mission controllers to delay the rover's planned activities and conduct detailed spectroscopic analysis. The visible and near-infrared spectrometer measurements revealed a substance with optical properties completely unlike any material in the existing catalog of lunar surface compositions. The spectrum showed strong absorption features at wavelengths, indicating the presence of complex silicates mixed with impact-generated glass, but also showed unexpected emission features in the near-infrared that suggested the material was either A, significantly warmer than surrounding regolith despite being in shadow, or B, composed of materials with unusual emissivity properties, inconsistent with known lunar mineralogy. The Chinese space program's characterization of this material as gel-like sparked immediate speculation, but official publications provided maddeningly sparse details. Researchers at the Chinese Academy of Sciences published a brief paper describing the spectral measurements but declined to release high-resolution images or provide detailed compositional analysis, citing ongoing research and data validation procedures. 3 years later, much of this data remains unpublished, fueling suspicions that the material's actual characteristics are too controversial to release without triggering unwanted scrutiny. Independent spectroscopists analyzing the limited published data have proposed various explanations, ranging from impact-melted glass with unusual chemical composition to exotic mineral assemblages created by space-weathering processes. However, none of these explanations adequately account for the apparent thermal signature, suggesting the material was warmer than its surroundings. On an airless body like the Moon, materials in shadow should rapidly equilibrate to the local thermal environment. A persistent temperature excess requires either an internal heat source or exposure to energy flux from an unidentified source. The most disturbing aspect of the gel-like substance discovery is not what was found, but what hasn't been investigated. Mission controllers directed U-2 to take spectroscopic measurements, but didn't deploy contact instruments to measure physical properties like viscosity, hardness, or exact temperature. The rover then drove away from the crater, never to return, despite the material representing the most anomalous discovery of the entire mission. This decision to document but not thoroughly investigate suggests either severe limitations in the rover's instrumental capabilities or a deliberate choice to avoid generating data that might be too controversial to interpret. The water question represents perhaps the most significant contradiction between NASA's historical claims and Chinese discoveries. For decades following the Apollo missions, NASA maintained that the Moon was bone dry, completely desiccated with water abundances at or below instrumental detection limits. This assessment was based on analysis of Apollo samples, showing no detectable water in lunar rocks and minerals. The absence of water became a fundamental constraint on lunar science, influencing theories of the Moon's formation and ruling out various geological processes. China's Chang'e missions have systematically demolished the dry Moon paradigm. The Chang'e 1 orbiter's microwave radiometer detected signatures consistent with water ice in permanently shadowed craters near the lunar poles. The Chang'e 4 lander's lunar penetrating radar found evidence of subsurface water/ice concentrations at depths of 12 to 40 meters beneath the South Pole Aitken Basin floor. Most dramatically, spectroscopic measurements by the Chang'e 5 lander detected water signatures in sunlit soil at mid-latitudes, regions where water should not exist, according to prevailing models of lunar surface chemistry. The water abundances measured by Chinese instruments aren't trace contamination at parts per billion levels. They indicate concentrations of approximately 120 parts per million in regolith samples, 50 parts per million in rock fragments, and potential ice deposits containing up to 30% water by mass in permanently shadowed regions. These concentrations are thousands of times higher than Apollo-era analyses suggested, and high enough to support future human missions using in-situ resource utilization. The obvious question demands asking, why did Apollo samples show no detectable water, while Chinese measurements find it abundantly distributed across the lunar surface? One explanation focuses on sampling bias. Apollo missions collected samples primarily from sunny equatorial locations, where any water would have been lost to space, while Chinese missions have specifically targeted high-latitude and permanently shadowed regions where water can survive. However, this explanation fails to account for the Chang'e 5 detection of water in sunlit mid-latitude soil, suggesting that water is more widespread and more stable on the lunar surface than Apollo-era theories predicted. A more controversial explanation suggests that Apollo sample analysis techniques, optimized for dry materials and conducted in laboratory environments that introduce terrestrial water contamination, may have systematically overlooked indigenous lunar water by attributing detected signatures to contamination rather than authentic lunar composition. If correct, this would mean that lunar water has been present in Apollo samples all along, but was dismissed as artifact, leading to 5 decades of incorrect assumptions about lunar chemistry. NASA's discovery of lunar water through the L-Cross impact mission in 2009 represented a partial acknowledgement that previous characterizations of the moon as completely dry were incorrect. However, the agency has been reluctant to fully embrace the implications of widespread lunar water, which would require substantial revision of lunar formation theories and acknowledgement that Chinese missions have advanced our understanding far beyond what Apollo achieved. The magnetic field measurements represent another area where Chinese data contradicts established models. The Apollo missions deployed magnetometers that measured the ambient lunar magnetic field at approximately 6 to 10 nanoteslas, roughly 100,000 times weaker than Earth's magnetic field, and consistent with theoretical predictions for a body lacking an active dynamo. However, the Apollo magnetometers also detected localized magnetic anomalies where the field strength increased by factors of 10 to 100, suggesting that crustal rocks retain magnetization from an ancient global magnetic field that existed when the rocks formed billions of years ago. The Chang'e missions have mapped the lunar magnetic field environment at unprecedented spatial resolution, revealing a far more complex picture. The Chang'e 2 orbiter's magnetometer measurements show that localized magnetic anomalies are not random, but appear concentrated in specific geological settings, particularly in the antipodal regions directly opposite the youngest large impact basins. The Chang'e 4 lander's surface magnetometer detected field strength variations correlated with time of day, suggesting that electrical currents induced in the subsurface by the solar wind create dynamic magnetic fields that vary on hourly timescales. Most controversially, the Yutu-2 rover's magnetometer recorded several brief events lasting 20 to 40 seconds, where the local magnetic field strength spiked to values exceeding 1,000 nanoteslas, more than 100 times stronger than the ambient field and inconsistent with any known magnetization of surface rocks. These transient magnetic pulses occurred without corresponding solar activity or external triggers, suggesting they originated from electrical discharge events in the subsurface or from magnetized materials being briefly exposed before being reburied by micrometeorite gardening. The Chinese research team that analyzed these magnetic pulses published their findings in Earth and Planetary Science letters, but carefully avoided drawing conclusions about the pulse's origin. The paper presents the observations, notes their statistical significance, and then ends with the standard academic platitude that further research is needed. The scientific community's response has been near total silence, with fewer than a dozen citations of the paper, despite its potentially revolutionary implications for understanding the moon's internal structure. If the transient magnetic pulses originate from subsurface electrical activity, this would indicate that the lunar interior is not the cold, inert environment that Apollo-era models describe, but rather contains electrically conductive regions, where charge separation and discharge can occur. Such electrical activity would require either residual heat, maintaining partial melting of interior materials, or presence of volatile compounds that enhance electrical conductivity, or mechanisms we haven't yet imagined. All of these possibilities contradict fundamental assumptions about the moon's thermal and chemical evolution. The seismic data collected by Chinese missions remains largely classified, but hints at discoveries even more controversial than the magnetic anomalies. The Chang'e 4 lander deployed a seismometer to the lunar far side, the first seismic instrument to operate on that hemisphere, and the first lunar seismometer to collect data since the Apollo 17 ALSEP package shut down in 1977. The Chang'e 4 seismometer operated continuously from January 2019 through at least December 2022, accumulating more than 4 years of data in a location never previously monitored. The Chinese National Space Administration released minimal information about these seismic measurements, publishing only a brief technical summary, noting that the instrument successfully detected moonquakes and confirming its operational status. However, analysis by international researchers monitoring the public data releases noted suspicious gaps in the published seismograms, periods where data should exist based on instrument operation reports, but where no seismic records were released to scientific archives. Dr. Renee Weber at NASA's Marshall Space Flight Center, who has studied Apollo seismic data for decades, requested access to the complete Chang'e 4 seismic dataset through international scientific exchange agreements. Her request was denied, with the explanation that the data was undergoing internal validation and quality assessment before public release. 4 years later, most of the data remains unreleased and fueling speculation about what the seismograms might reveal. Leaked summaries from researchers with access to preliminary Chang'e 4 seismic data suggest the records contain events unlike anything in the Apollo seismic catalog. The Apollo seismometers recorded 3 types of moonquakes: deep moonquakes occurring 700 to 1,100 kilometers below the surface and triggered by tidal stresses from Earth; shallow moonquakes occurring in the upper crust from tectonic adjustments; and impact events from meteorites striking the surface. The Chang'e 4 seismometer allegedly detected a 4th category: episodic seismic events occurring at intermediate depths of 200 to 400 kilometers with frequency content suggesting fluid movement rather than brittle fracture of rocks. If these leaked descriptions are accurate, they imply the existence of partially molten regions at depths where the moon should be completely solid, according to thermal evolution models. The presence of mobile fluids would require either far higher internal temperatures than predicted, or the existence of volatile compounds that remain liquid at much lower temperatures than pure silicate melts. Either possibility demands fundamental revision of our understanding of the lunar interior. The Chang'e 5 mission's orbital observations before its landing phase detected something even more inexplicable. The orbiter's neutron spectrometer, designed to map hydrogen distributions that might indicate water ice, recorded anomalous neutron absorption features in specific locations within Oceanus Procellarum. Neutron spectroscopy works by detecting how cosmic ray interactions with surface materials produce secondary neutrons. Hydrogen-rich materials like water ice absorb neutrons efficiently, creating detectable signatures. The anomalous features detected by Chang'e 5 showed neutron absorption consistent with hydrogen concentrations of approximately 1,000 parts per million in specific locations measuring 2 to 5 kilometers across. However, these hydrogen-rich regions occurred in areas receiving full sunlight where water ice cannot persist. The hydrogen must therefore exist in chemical compounds stable at lunar daytime temperatures exceeding 120 degrees Celsius, compounds that shouldn't exist in lunar surface materials, according to current understanding of lunar chemistry. One possible explanation involves hydroxyl groups chemically bonded into mineral structures through interactions between solar wind protons and oxygen-bearing minerals. This mechanism can create hydrogen abundances of perhaps 50 to 100 parts per million, but the concentrations measured by Chang'e 5 exceed this by an order of magnitude. The excess hydrogen requires either a delivery mechanism far more efficient than solar wind implantation, or indigenous hydrogen incorporated during the rock's formation. Hydrogen that should have been lost during the moon's formation if current models are correct. The alternative explanation that nobody wants to discuss openly is that the hydrogen signatures might indicate subsurface water reservoirs, covered by thin layers of regolith. If such reservoirs exist in sunlit regions, they would require continuous replenishment to balance loss through diffusion and photolysis, implying active outgassing from the lunar interior. This would mean the moon is not geologically dead, but continues to release volatiles from depth, contradicting 50 years of conventional wisdom. The age controversy extends beyond just the Chang'e 5 samples. Detailed crater counting analysis of Chang'e landing site imagery reveals systematic discrepancies between crater-derived ages and radiometric dating results. Crater counting uses the density and size distribution of impact craters to estimate surface ages, relying on calibration curves established using Apollo sample ages. The technique assumes that the impact rate has remained relatively constant over lunar history, and that crater formation processes are well understood. Chinese researchers applied crater counting methodologies to high-resolution images of the Chang'e 5 landing site before samples were returned. The analysis predicted surface ages of approximately 2.5 to 2.8 billion years based on crater densities. When the returned samples yielded radiometric ages of 1.97 billion years, the 600 to 800 million year discrepancy suggested that either the crater counting calibration is systematically wrong, or the impact rate has varied more dramatically than models assume, or crater formation and destruction processes operate differently than current theories predict. The implications ripple outward to affect age estimates for terrains across the entire moon and potentially across other airless bodies in the solar system. If crater counting systematically overestimates ages by 30 to 40%, as the Chang'e 5 results suggest, then large swaths of the lunar surface may be significantly younger than previously believed. This would extend the era of lunar volcanic activity, require higher internal temperatures persisting longer into lunar history, and potentially indicate ongoing geological processes even in the present day. Western planetary scientists have responded to this challenge with various technical arguments about crater counting uncertainties, regolith mixing effects, and statistical limitations of small sample sizes. However, these responses feel more like defensive rationalization than genuine engagement with anomalous data. The fundamental question remains unanswered. Why do crater counts and radiometric ages disagree so dramatically for the Chang'e 5 site when they align reasonably well for Apollo sites? Now, one unsettling possibility is that the Apollo mission sites were deliberately selected to sample terrains where crater counting and radiometric dating would agree, creating a false impression of methodological validation. If Apollo site selection prioritized locations where independent age estimation techniques converged, this would produce a biased calibration dataset that works well for similar terrains but fails when applied to geologically different regions like the Chang'e 5 site. The Chinese missions, selected purely for scientific interest without concern for validating existing methodologies, may have inadvertently revealed systematic biases in techniques that planetary science has trusted for half a century. The composition of the Chang'e 5 samples revealed another surprise that contradicts Apollo-based understanding. The samples contain unusually high concentrations of creep, an acronym for potassium, K, rare earth elements, REE, and phosphorus, P, materials that trace their origin to the final stages of the lunar magma ocean's crystallization. Creep is typically concentrated in specific regions near the Procellarum creep terrain, and its presence elsewhere was thought to result from impact mixing. The Chang'e 5 samples show creep signatures combined with rock ages of 1.97 billion years, indicating that creep-rich magmas were still being emplaced on the lunar surface nearly 2 billion years after the lunar magma ocean supposedly solidified. This temporal association suggests either that isolated pockets of creep-rich material remained molten in the deep lunar interior for over 2 billion years, or that creep components were remobilized and transported to the surface through processes we don't understand. The prolonged existence of molten creep reservoirs requires heat sources beyond the radioactive decay of uranium, thorium, and potassium that drives most planetary internal heating. Tidal heating from Earth's gravity provides negligible energy to the Moon due to the synchronous rotation that always keeps the same face toward Earth. No other conventional heat source can maintain partial melting for the required duration. Some Chinese researchers have quietly suggested that the solution to the heat problem might involve exotic processes like core crystallization, releasing latent heat, or phase transitions in mantle minerals, releasing stored energy, or even more speculative mechanisms involving neutrino interactions or dark matter annihilation. These suggestions rarely appear in peer-reviewed Western journals, but circulate in Chinese language publications and conference presentations, hinting at theoretical explorations beyond what Western planetary science considers acceptable. The Chang'e 4 mission's observations from the far side revealed asymmetries in lunar properties that Apollo observations from the near side never suspected. The lunar far side is dramatically different from the near side. It has thicker crust, fewer Maria basins, more intense cratering, and different crustal composition. These asymmetries have been known since early Soviet and American robotic missions photographed the far side in the 1960s, but their origin remains controversial. The prevailing theory suggests that the asymmetries result from the giant impact that formed the Moon itself. In this model, the Moon formed from debris created when a Mars-sized body struck the early Earth approximately 4.5 billion years ago. The debris coalesced in orbit, with one side facing Earth and experiencing different cooling and tidal conditions than the far side. However, this theory struggles to explain why the asymmetries are so extreme and why they persist in properties like crustal thickness and composition that should equilibrate over geological time. Chang'e 4's measurements of far-side crustal composition using ground-penetrating radar and spectrometers revealed that the asymmetry is not limited to the surface, but extends deep into the crust and possibly the mantle. The far side shows systematically higher abundances of thorium, uranium, and other heat-producing elements in the lower crust, suggesting that radioactive elements became concentrated in the far side during the Moon's differentiation. This concentration would produce more internal heating on the far side, yet the far side shows less volcanic activity than the near side, exactly the opposite of what would be expected. The paradox of far-side heat sources without far-side volcanism has no satisfactory resolution within current lunar science. Some researchers propose that the far side's thicker crust prevents magma from reaching the surface, even though heat production is higher. Others suggest that the radioactive element concentration measurements are incorrect or misinterpreted. A third option, and rarely discussed in public but circulating in private conversations, suggests that some process actively transfers heat from the far side to the near side, possibly through convection cells in a partially molten mantle that current models claim cannot exist. The mineralogical differences revealed by Chang'e mission spectroscopy further challenge Apollo-based paradigms. The visible and near-infrared spectrometers carried on Chinese orbiters and landers have identified mineral assemblages that don't match the compositional types established from Apollo samples. Particularly puzzling are detections of hydrated minerals, clays, and other compounds incorporating water or hydroxyl groups in their crystal structure, in locations where such minerals shouldn't survive the harsh lunar environment. Hydrated minerals on Earth form through water-rock interactions and typically decompose when heated above 300 to 400 degrees Celsius. Lunar daytime temperatures reach 127 degrees Celsius, high enough to be uncomfortable for hydrated minerals, but not immediately destructive. However, over billions of years of repeated thermal cycling between 127 degrees Celsius in sunlight and minus 173 degrees Celsius in shadow, any hydrated minerals should decompose and release their water, leaving only anhydrous minerals behind. The persistence of hydrated minerals detected by Chinese instruments suggests either that the minerals formed recently on geological timescales, or that some mechanism continuously replenishes water to replace what is lost, or that the minerals are protected in microenvironments where decomposition rates are dramatically slower than surface conditions would suggest. All of these possibilities conflict with the standard model of the Moon as an ancient, inert body, where surface materials have reached equilibrium with the space environment. The discovery of novel mineral phases in Chang'e 5 samples has generated perhaps the most concrete challenge to Apollo-era mineralogy. Chinese researchers identified a new mineral dubbed Changesite-Y-, a phosphate mineral containing rare earth elements including yttrium. The mineral forms columnar crystals, approximately 10 micrometers in size, and has a composition and crystal structure that don't match any previously known mineral from lunar or terrestrial samples. The significance extends beyond simply adding a new entry to the mineral catalog. Changesite-Y requires formation conditions, specific temperature, pressure, and chemical environment, that don't match any process documented in Apollo samples. The mineral's presence implies that the magmas that produced the 1.97 billion-year-old Chang'e 5 basalts had different compositions, evolved through different crystallization paths, or formed under different conditions than the older basalts sampled by Apollo missions. One possibility is that the Chang'e 5 basalts represent late-stage differentiation products from a magma source that had undergone more extensive chemical evolution than the source regions for Apollo basalts. This would require that magma generation continued in the lunar interior far longer than Apollo data suggested, allowing more time for chemical differentiation to produce exotic compositions. Alternatively, the Chang'e 5 source region might have had fundamentally different initial composition, suggesting chemical heterogeneity in the lunar mantle far exceeding what Apollo samples indicated. The refusal of NASA and Western research institutions to actively pursue collaborative analysis of Chang'e samples represents a troubling departure from the ideal of international scientific cooperation. When China offered to share Chang'e 5 samples with international researchers through formal exchange agreements, NASA declined to participate due to restrictions in the Wolf Amendment, U.S. legislation that prohibits NASA from bilateral cooperation with China without explicit congressional approval. This political barrier means that the most advanced analytical instruments in American laboratories, tools that could provide isotopic, chemical, and mineralogical data far exceeding what Chinese facilities can currently produce, are not being applied to study samples that represent the youngest lunar materials ever collected. The lost scientific opportunity is staggering, but the deeper concern is that Western lunar science is proceeding with incomplete information, building models and theories based primarily on Apollo data, while ignoring contradictory evidence from Chinese missions. The scientific community's asymmetric treatment of Chinese discoveries reveals uncomfortable biases. When Israeli researchers announced possible detection of water ice by their Bereshit lander before its crash in 2019, the finding received extensive Western media coverage despite being preliminary and unconfirmed. When Chinese missions detected water with far higher confidence levels using multiple independent instruments, the Western scientific press treated it as a marginal curiosity rather than a paradigm-shifting discovery. Similarly, when India's Chandrayaan-1 mission confirmed the presence of water molecules on the lunar surface in 2009, NASA promoted the finding extensively and credited the American-built Moon Mineralogy Mapper instrument carried on the Indian spacecraft. When Chang'e missions made comparable or superior measurements, the results were either ignored or grudgingly acknowledged, while emphasizing uncertainties and limitations. This double standard extends to theoretical modeling. When Apollo data suggested the Moon was dry and geologically dead, models were constructed to explain why this must be the case, and these models became established paradigms taught as settled science. When Chinese data showed water, young volcanism, and possible ongoing geological activity, the Western scientific community responded not by revising the models, but by questioning the data quality, suggesting alternative interpretations, or simply ignoring results that didn't fit preconceptions. The geopolitical dimension of lunar exploration introduces motivations that have nothing to do with scientific truth. During the Apollo era, the moon was an arena for Cold War competition, and American success in landing humans represented ideological victory as much as scientific achievement. The narrative of the moon is conquered, understood, and no longer worthy of major investments served political purposes by justifying the redirection of NASA resources toward other priorities, like the Space Shuttle and International Space Station. China's lunar successes threaten this narrative by demonstrating that the moon is not fully understood, that major discoveries remain to be made, and that the nation leading lunar exploration in the 21st century may not be the United States. This creates institutional and political pressure to minimize Chinese achievements, maintain that Apollo-era understanding remains fundamentally correct, and avoid acknowledging that American lunar science may have been incomplete or biased. The question of who controls the narrative about the moon has implications extending far beyond academic debates about geology and chemistry. As multiple nations plan permanent lunar bases, mining operations, and use of lunar resources, the nation perceived as the authoritative source of lunar knowledge gains substantial advantage in setting standards, claiming territory, and exploiting resources. If Chinese missions are revealing fundamental truths that NASA missed or ignored, this shifts the balance of lunar expertise and authority away from Western institutions. The future of lunar science requires confronting these uncomfortable realities. Either the contradictions between Apollo-era paradigms and Chinese discoveries result from instrumental differences, sampling biases, and interpretational nuances that can be resolved within existing frameworks, or they indicate that fundamental aspects of lunar science need revision. The stakes are too high for political considerations to override scientific integrity. We stand at a crossroads. The comprehensive data set from Chinese lunar missions, spanning orbital observations, surface measurements, sample returns, and geophysical monitoring, presents a picture of the moon that is more complex, more active, more chemically diverse, and more mysterious than the simplified narrative that emerged from Apollo. The question is whether Western science will engage honestly with this new picture or continue to protect established paradigms against contradictory evidence. The universe doesn't care about our political systems or national rivalries. The moon is what it is, regardless of which nation's instruments make the measurements. If Chinese missions have revealed aspects of lunar reality that challenge Western assumptions, the scientific response should be curiosity and investigation, not defensive dismissal. The pattern repeating throughout this analysis is clear. Chinese measurements consistently reveal more complexity, more activity, more water, more recent volcanism, and more ongoing processes than Apollo data suggested. This pattern could mean that Chinese instruments are systematically biased toward false positive detections. Or it could mean that the simplified dead moon paradigm was always an incomplete picture, and we're only now beginning to see the full reality. The choice before the scientific community is whether to follow the evidence wherever it leads, or to protect comfortable assumptions that make the moon simple, predictable, and safely understood. History suggests that nature always proves more complex than our theories predict. The humble approach is to accept that decades-old paradigms built on limited sampling of a single hemisphere might not capture the complete truth about a world we're only beginning to truly explore. What Chinese lunar missions have found on the moon contradicts core assumptions about its age, chemistry, water content, internal structure, and geological activity. These contradictions cannot be dismissed as instrumental artifacts or interpretational differences. They represent genuine challenges to established knowledge, challenges that demand revision of theories that have stood for 50 years. The cosmos is indifferent to human pride. The moon exists in its actual state regardless of what our theories claim. Chinese missions are revealing that actual state with increasing clarity and detail. The question is whether Western science will embrace these revelations and advance our collective understanding, or whether institutional inertia and geopolitical rivalry will prevent the synthesis of knowledge that truth requires. The message is clear. The moon we thought we knew was a simplified approximation, and the real moon, complex, active, and still full of mysteries, is only now coming into focus through the instruments deployed by China's patient, systematic exploration program. The universe is watching how we respond to this knowledge. Our scientific integrity and commitment to truth over politics will define whether we deserve to call ourselves seekers of knowledge or merely defenders of convenient narratives.